Assalamu alaikum, this is Sayyid Shahir. In this video, I'm gonna share an overview of our final year project. Moisture content in grains is a crucial parameter in agriculture, directly impacting storage stability, crop yield, and overall economic value. Traditional moisture detection techniques fall into two main categories: direct and indirect methods. Direct methods, while accurate, are often slow, labor intensive, costly, and require skilled operators, making them impractical for real time applications. Indirect methods, such as contact-based sensors, introduce the risk of contamination or physical damage to the samples and typically lack the flexibility needed for rapid, large-scale assessments. Non-contact indirect techniques, though addressing some of these issues, are often expensive and less adaptable to different grain types or varying environmental conditions.
Our proposed solution utilizes the concept of orthogonal frequency division multiplexing, called OFDM, implemented with the help of software-defined radio USRP kits, which help us to send RF signals and record them at the receiving end. With the help of those signals and subcarrier data or OFDM, we can train our AI algorithms, which can help us to detect different moisture levels and also classify them.
The objectives of our final year project are as follows. Our project general methodology can be divided into four major steps.
This is our experimental setup. This side is the transmitter side and this side is the receiver side.
System design responsible for our transmitter and receiving of wireless signals.
Now this is the transmitter side of our project. From here we will run our code of transmitter OFDM frame. Now this is the wireless channel path: transmitter antenna, transmitter USRP, receiver USRP kit. The parameter of these devices are defined over there in our LabVIEW code. Now the receiver parameters are adjusted over here. The carrier frequency and IQ rate should be the same of both transmitter and receiver. The time frame of our data collection sample is 10 seconds. From here, let's run our code.
This is the raw data that we have recorded. Now we will pre-process it in MATLAB and perform our classification task. These activities are repeated for different classes and for several number of times. The following signal processing steps are followed to extract useful data subcarriers from wireless channel state information. The output of each step can be seen in the next visualizations. This is the final visualization of all the steps that was mentioned earlier. So these steps are performed for each file within our data set. This is how the data set is structured with manual feature extraction. And how it is structured: the columns represents different 36 features from time and frequency domain, and the last column represents the class label. Now if you are wondering what are the class label, so basically the class labels here are different level of moisture. A brief overview of our experiments, data analysis techniques, classification algorithms, and evaluation matrices. The architecture diagram for best performing algorithms with manual features as their input. This is the architecture diagram of our approach, which is based on custom 2D CNN architecture and multi-layer perceptron. This approach doesn't use the manual feature extraction. Instead, it utilizes the power of 2D CNN custom architecture to extract the features and that fed into the MLP for the further classification purpose. The input dimension to 2D CNN is 100 cross 148, while each cell doesn't represent an intensity level. Instead, it uses the magnitude response values. As it can be seen in the results that our 2D CNN approach outperforms the best fit algorithms and manual feature computation.